All right, good morning. So today we'll be starting lecture number 20 with a different topic called sequence modeling. So just as a slight recap, since we started neural networks, we have gone through what we called as artificial neural networks, but specifically they were just multi-layer perceptrons. I just wanted to keep the naming convention similar to what we discussed later, so we called those as artificial neural networks. After that, we looked through CNNs, which was convolutional neural network. And they were specifically designed for images because of that idea of 2D spatial correlation that exists in vision. So anything with respect to image processing, for instance, is something that could be done by CNNs, convolutional neural networks. We didn't discuss about it, but you can extend 2D CNNs to a 3D format. So if you have videos as your data, then 3D CNNs is something that you would have looked at. Today what we'll discuss, or at least we'll start discussing, is the idea of sequence modeling and the next kind of neural networks, which is going to be RNNs, or recurrent neural networks, and a couple of its variants. So we'll start with discussing those concepts for today and probably end it on Wednesday. So it'll be about 2 lectures for sequence modeling. And for today we'll go through just getting an intuition as to what sequence modeling is going to be, and going through exactly what we did with the other neural networks, which is, okay, we have something like a very simple MLP. A multi-layer perceptron works on any kind of data, right? It's basically just connecting all inputs to some hidden layer and then to a certain output. But there are going to be limitations of using something like that for sequence modeling, similar to what it was for CNNs, and for vision. So we'll go through some limitations of it, followed by recurrent neural networks, and some kind of variants of recurrent neural networks, which is the LSTMs and GRU units, followed finally by the temporal convolutional network. On Wednesday, we'll go through a different kind of a model called transformer, but also very similar to what we are going to be discussing today. All right, with that, we can start with the idea of sequence modeling. Very simply put, it means that your input data is part of a sequence. In vision, for instance, we assume this concept of IID. You have seen a couple of these words before, but that was basically when we discussed, like, in the very beginning when we were talking about logistic regression. The idea was that all input data that is coming in is identical, is independent, and identically distributed. The first word there is important. The first I stands for independent, which means that if I have a batch size of, let's say, 20, my first image is independent of the second image. Technically, that is essentially what your IID input is telling you. But that might not be true. And in most cases, it is not true. Generally, you have a specific distribution from which you have sampled this kind of data, and there is going to be some kind of correlation amongst your data. But we start off by assuming IID. In these kind of sequence modeling, this means that the features that are coming in that we'll be using to consider or create our network are not independent. They're all present within some kind of a context. Speech is the easiest and the best example for sequence modeling. So, when I'm talking like this, I've been talking for what? Maybe the last 4 minutes, and most of what I've said is connected to each other. Most of the sentences are particularly flowing one after the other, and there's a certain kind of meaning to all of them, right? So to understand what I'm saying now, hopefully you would have been concentrated from 3 minutes back, which is where the sequence modeling will commence from. So take this, the first table over here. You have age, sex, occupation, and income. This is the kind of features that we started off with, the tabular data that we started off with in our lecture number 2 and 3. There's no this feature data, for instance, there's no dependence in terms of time. The easiest way we can consider or understand sequence is by this idea of time dependence. As I said, in speech, the last 5 minutes or 4 minutes I've been speaking, and there is some kind of a correlation with respect to time. So what I said 1 minute back, for instance, is more relevant to what I'm saying now versus something that was like 4 minutes ago, right? So there is a time dependence in terms of speech signals that is very important for this kind of sequence modeling. In other things as well, like temperature, stock exchange, language, which is speech, this kind of time dependence is very important with respect to what our features are going to be. So interrelationships between data points are not modeled by all the classical ML algorithms that we have talked until this point. Which technically are also offshoots of these multi-layer perceptrons. But in sequence modeling, this is going to be very important. So sequence modeling by itself is not an application. Sequence modeling is a topic. The reason I say that is because within sequence modeling, we'll go through very similar applications like what we did. For instance, classification is something that we did for vision, right? It was an application within these CNNs or within these neural networks. Similarly, within sequence modeling, we'll have classification as an application. We'll have sequence generation as applications, sequence-to-sequence prediction as applications, and so on. So the main takeaway from this slide is that you shouldn't consider sequence modeling as an application, but rather it is a topic, it is a concept on top of which we can construct other kinds of applications. So for instance, this kind of classification, and this is very important, some kind of ECG signals, let's say your heart rate. In signal processing, this is a very common example that we use. There are 4 stages in your heart rate that is that's always going to be sequentially present. So these particular thing, it's called like PQRS. I think I'm not really sure. I've forgotten which part of this is P. This is probably Q. Let's say this is R, and this S. So there are specific ways in which your signal goes up and goes down in this particular case, and that is repeated over time. It's cyclical, it's periodic in nature. But the regions, the P, let's say, which is a slight increase from what it was before, and then you have a huge increase, which is going to be this region over here, right? So this is going to exist across time. It is going to be cyclical, it's going to be periodic. The way you would detect some problem exists in this signal is basically by saying that, okay, maybe your Q is not acting the way it needs to, in which case maybe there is some kind of a heart issue, atrial fibrillation, or any other kind of issues that might exist in these ECG signals, right? So in this case, you need to know about P, Q, R, and S, the fact that they all exist together, and the fact that they exist one after the other. So this is kind of you require this modeling before you can do some kind of a classification and say that maybe Q, the region of Q, is not in the right position, in which case you would be doing some kind of anomaly detection in ECG signal, which is basically a classification that the current signal is some type of an anomaly. Same thing with sentiment analysis as well. I think we saw this example back in lecture number 3, where you're looking for certain words, and based on the place where those words exist, you can say whether a review of a movie is either a positive review or a negative review or so on. So essentially you're modeling a sequence, and based on that modeling, you are going to be then assigning some kind of a classification score for this particular sequence. Same thing with temperature forecasting and DNA sequence classification as well. So that's like the first application, which is the idea of classification. The next one is sequence modeling, where we'll be discussing about sequence generation. So sequence generation is the easiest one, I can say, is image captioning, for instance. So image captioning is the application where you are given an image, and then you are asked to create captions for this particular image. So for instance here, I don't know if you'll be able to see this, but you have this image of a baseball. So the man in gray swings a bat while the man in black looks on, which is essentially describing a sequence modeling network is describing what is happening within this image. Same thing here as well. On the right hand side, a big bus sitting next to a person. Maybe this is incorrect, maybe it should have been the opposite, a person sitting next to a big bus, but again, we are not discussing the validity of these captions. We are just discussing the fact that these are applications that can be constructed that is based on sequence modeling. So any kind of new generative algorithms, if you want to summarize a particular image, if you want to summarize any kind of 2D or 3D data, and you're using an LLM or a large language model to generate this text, what you're actually doing is sequence modeling as a concept, and then sequence generation is the application that is going through. Same thing with handwriting recognition generation and music generation as well. You are basically generating a certain set of sequences, which is going to be part, or which is an outcome of sequence modeling. So sequence to sequence generation, generally when we talk about classification, we discuss that given a large amount of data, whether it is number of pixels or a paragraph or let's say a book, you want, or a review for instance, you want a certain word for it. Like if it's a review, your goal is to say whether it's a positive review or a negative review. If it's something like what we discussed before, which is this kind of anomaly detection, your goal is to say whether it's an anomaly or not an anomaly. So in sequence generation, on the other hand, the idea is similar to an autoencoder, where instead of having a single output, you have the same length sequence as the output. So in this case, for instance, in English, you can have this kind of a statement, and you can translate it to a different language altogether and have a completely different sequence that means the same thing, but it's now in a different language. And this could be very different. For instance, English, we always write from left to right. Something like Urdu, for instance, is going to be from right to left, which is a completely different way of language generation, and yet it needs to do something like this in this application of sequence to sequence generation. Same thing with the text summarization as well. Given a large source text, in this case it's a single sentence, but the goal in summary is to maybe summarize what this sentence is into a smaller set of words. Of course, this is the easiest and most trivial way of summary, which is basically recognizing which is the most important parts in a sentence and reproducing those same results, and taking out all the, took a taxi to the night, in the, while in the party, and so on. It's basically just a set of words which we'll be using for this kind of summary. Again, this is all part of sequence to sequence generation as application, rather than something like classification or generation that we, or just a basic sequence generation that we did before. All right, so now we'll talk about the methodologies of doing sequence modeling itself. And I didn't even put a slide for what MLP sequence modeling is, because hopefully by now you should be able to visualize the multi-layer perceptron. So given, let's say, this kind of a text, a multi-layer perceptron, what it does is basically for the character P, there is a weight W1 associated with it. For E, there is a weight W2 associated with it. With 3, there is a weight W3. For T, there is a weight W3 associated with it, right? So essentially think of it as pixels. These characters are pixels in your sequence modeling, and your MLP is doing something like this. So if you remember when we were talking about MNIST dataset, you have an image with, let's say, an image 8, and there's a 28 cross 28 image, which basically, if you take that into a vector, it's going to be 784 cross 1. So an MLP, or a multi-layer perceptron, basically considered this as just one vector, on top of which you had like, I don't know, this was 784 cross 1. Then your next layer would be something like 200 cross 1, let's say, number of neurons. So basically every single element is going to be fully connected to the next layer there, right? So an MLP you should think of as exactly similar here as well. Here, this element here was a single pixel that is connected to a weight. In this case, P would be the pixel. P would be the character, which is the smallest token in this particular case, which would be W1, W2, W3, and so on. So every single character is now connected to a weight, and that is essentially what an MLP is going to be. But this MLP is not easy to design for exactly the same reasons as before. The most important parts is the difference from the CNNs, of why we moved from CNNs from MLPs, we moved to CNNs, right? Now we'll be doing the same thing. From MLPs, we will be moving to some other kind of architecture, let's call it RNNs. The reason we do that, the first main one, is that the input and output lengths must be fixed at training time. And this is not easy at all. In images, it's kind of manageable to do this, because you have a 1080p image, which let's say is 1080 here and a 1440 in terms of the height and width. if you have this image, you can downsample this. So you might have noticed that whenever you use some kind of pre-trained ImageNet architectures, you always downsampled it to 224 cross 224. And you can do this. You can downsample it and still have the same, perceptually it'll still be the same image. Yes, it'll be smaller, and when you try to view it on a HD screen, it's not going to be as good looking, but it's perceptually still the same image. But you cannot do this in language, in terms of natural language processing. The reason being that, think of what it means to downsample a 1080p image to something like a 224 cross 224. You are taking out these letters in middle. So E will be deleted, T will be deleted, E again will be deleted, right? So what you'll have here is nothing more than P and R. And that means nothing. If this were an image, it would be okay to remove a few pixels and you would still be able to see what the image is. But if I take Peter and I remove E, T, and E, I only have a P and R. So there's no way to downsample. There's no easy way to downsample your data when it comes to language. And hence, the first point here, it completely takes away our usage of MLP for these kind of sequence modeling, because I need to create these, think of how you design your MLPs, right? You start with defining the number of input pixels and then the hidden layer representation. So something like 784 cross 200. You design something called an n.linear, and this is essentially your MLP, at least the first layer of your NLP. To do this, you need to know the 784, but you're not afforded that opportunity in language because you'll never know how much a sentence is going to be, right? So there's also different ways of the same sentence. It could be in an active voice and a passive voice. And that's why MLPs is never you cannot think of it as a possibility as well when we are discussing these kind of sequence models. The last 2 points are actually, in the limitations slide, the last 2 points are similar to what we had before. So in this case, overfitting is going to happen, especially when we don't have as many data points. And the last one is that words can change positions and can have the same meanings or different meanings. Active and passive voice is a very simple way of expressing this issue. But these two exist in vision as well. But this one here is limitation specifically for RNNs, which is very, very hard to overcome for MLPs. So how do we change it? Today we'll talk about 2 ideas. The first one is similar to CNNs, which is we're going to be doing some kind of a parameter sharing within our neural network. Because think about this sentence here. I went to Japan in 2009. My name is John. In 2009, I went to Japan. So actually, the first sentence and the second one is not adding anything. So just think of the second part. In 2009, I went to Japan. So the 2009 part, which is essentially our, let's say, our template or our kernel, can now convolve and see where the number is essentially. So it wouldn't matter if 2009 is at the latest stage of a sentence or in the beginning of a sentence. You'll still know that the number 2009 is going to exist, and that might be the answer if the application you're looking at is something like a visual question answering application. In fact, it's kind of similar to when we were doing convolution. We had this invariance principle where it doesn't matter if cat is on the right-hand side of an image or on the left-hand side of an image, it should still be cat. Right? This is what we saw, I believe, when we talked about convolution. We had this image of Einstein, and then we had this eye, and we were convolving around it to check where the eyes are. And that is going to be similar to the 2009 in language processing we can do. So that is about parameter sharing, which is again very similar to CNNs. The next one, which is what we're going to start with, and probably more important, is the idea of state history, where when we discuss vision applications, we have always had the output, let's call it y equals f of x, where f is, of course, a very complicated, let's say, a neural network that could be 152 layers in your ResNet 152. But essentially, it's still this kind of a function. Given an input x, I can give you an output y. But the goal in sequence modeling is that your X is not just independent of itself, right? The current input, the sentence I'm saying now, is going to be dependent on the previous sentence. So I need my present X of t and some function of my previous sentence, which would be h of t minus 1. And that is what state history essentially means, which is that I need to keep track of how my inputs have changed over time. And it could be very simple, right? It could just have been an x of t minus 1 as well. But when we say h of t minus 1, it's basically a hidden layer within the neural network is what we are referring to. So it's not just a sentence that I said previously, rather it is how that previous sentence has been processed within a neural network that will now be used as an input along with my current sentence to give the current output at this stage. Maybe I shouldn't say output, I'll adhere to the words that are here. So state vector at present time. So I'm going to call the representation as state vector in this particular case. So representation is the same thing. In CNNs, when we had talked about it, it's the latent representation within the autoencoder is what we're going to be discussing as state vector in this particular case. So at present time, h of t is a function of state vector at past time, which is h of t minus 1, and the input at present time, which is x of t. Again, it'll be easier if you try to differentiate it from all the vision applications by thinking of it as instead of y equals f of x, it's basically y of t is equal to something like f of y of t minus 1 comma x of t. Of course, by putting in h, we are actually kind of saying that it could be something that exists within a latent representation within the neural network. If you read through any literature, then you're going to see this kind of flowchart where basically they show you something like this, and then we unfold it to have multiple states within my neural network, and it's stating exactly this. The same equation is being stated in a pictorial form over here, where x of t minus 1, x of t, and x of t plus 1, these three here are my inputs at different times, and they're going to be passed through to a neural network. Rather than looking at each input individually, it's going to be looking at, let's say at h of t minus 1, it's going to be, it has two inputs. It has x of t plus 1, at h of t plus 1, it has two inputs, which is x of t plus 1 and h of t. And both of these inputs are going to be represented in this fashion. So I'll come back to this kind of a diagram in the next slide, essentially. But the reason that this is going to be good, or this is important, this state history, is that is because of these three things that we have over here. So the most important one is that the input sequences themselves can be of varying lengths. So a sentence is not always restricted to, let's say, 10 words. We have liberty in terms of choosing the number of words, the number of characters that are going to be in our sentences. So it's very important that our input sequences themselves should be of varying lengths. And by making this kind of architecture where we are saying that x of t plus 1 exists from, h of t plus 1 is going to be dependent on h of t and x of t plus 1, and h of t now is dependent on h of t minus 1, and so on. So until h of 0, it could be dependent on it. Again, this is something that we can decide later, how much it needs to be dependent on. But now we can say that it has to be dependent on a certain amount. And we need to take care of that, basically, during the backpropagation algorithm, but we will be able to do that in a bit. So this idea of state history is the main driving factor underneath these kind of RNNs, which are recurrent neural networks. So most sequence modeling problems are going to be solved by using some combination of, or maybe not solved, but are going to be modeled by some recurrent algorithms or recurrent parts of a neural network, which is given by this kind of architecture that you generally see in your literature. So before I stop, just to see if there are any questions, I just want to go through this one slide, which basically is going to discuss what the basic architecture is going to be. What we have in simple CNNs or MLPs when we were doing vision is this one here on the left hand side without this part. So this part would not have been there when we discussed the vision architectures from before. Given in X, we had some kind of hidden layer representations that you would then get some kind of outputs, and then you would use that in order to construct a loss function. Based on some kind of ground truth, you would have this kind of a loss function. You would back propagate it, so the gradients would flow through here, 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 and so forth. So that would be one epoch or one iteration within your back propagation, and you would do more and more within it, right? So that is the main part of a CNN, or that's the main idea we had before with CNN. But the architecture in this kind of RNNs is going to be different. You are going to be unfolding this H, which essentially means that you will have an HT minus 1, HFT plus 1. So think of this as during backpropagation, we will have 3 different iterations or 3 different loss functions within the same iteration. And it takes a little bit of intuition to understand this. So essentially that means that in a single iteration of your backpropagation, and I'm using the word iteration here, not epoch, a single iteration of your backpropagation, given a single data point or one sentence as your input, what you need to consider is that this sentence has, let's say, 3 letters. So maybe it's not a sentence, it's a single word, let's say THE. So this particular word essentially passes through this recurrent neural network. And if you think of each character as its own input, your THE, so your recurrent neural network is going to take, let's say, T in the beginning, multiply it with some kind of a simple matrix U, which in this case is going to be something like an MLP, just a very straightforward MLP, to get your hidden layer representation HFT minus 1. It is again going to be multiplied by some weight vector that is W to get HFT minus 1, which would then be passed on to HFT. And it is again multiplied by another matrix V in order to get your output, right? So if this were an autoencoder, you would basically have U multiplied by X, and then whatever this is, H would then be multiplied by V, let's say, to get your output. That is going to be X cap, right? Which is exactly the same as this portion of your RNN, where you're multiplying it by a certain set of weights, which is U, to get a hidden layer representation H. And this H is again going to be multiplied by V in order to get back, it's not X cap in this case, but it could be something like what we discussed before, where it's translation. This word needs to go to Urdu, where it has to move to a different language, and maybe a complete opposite as well. Instead of left to right writing, it has to be right to left. But still, your output in this case is going to be a different language, right? But essentially what you're doing is you're just multiplying your U and V as these 2 matrices. The difference here is in this additional weight that we're going to call W, which is going to be multiplying my current HFT minus 1 and transfer it over to HFT, is the main difference that exists between what we had discussed before versus what we are discussing now. Of course, this is just for one T, but you would have to do the same thing for H here as well, which is the next input. You would have to do the same thing for E as well, which is the input after that. So all of these multiplications have to occur based on these characters, based on these sequences that is going to exist. So on the right hand side is more of a, you have your X, which is your input, H is your hidden layer representation or hidden state, O is your output. Again, we are only showing a single matrix here, U and V, but it could be different layers. It's U1, U2, it could be any number of layers that can exist between these points here. And there's a loss function L, some target, which is our ground truth, and U is our mapping from input to hidden state, W is mapping from present hidden state to future hidden state, and V is a mapping from present hidden state to present outputs. Any question in terms of the architecture itself? So this is important. You'll have one question in your homework 7 that is going to be based on RNNs, designing these kind of architectures and backpropagating it within the framework. Again, the only difference is the existence of this hidden state that is going to be connected to each other. At every single point, there is going to be some kind of a connection between the current hidden state to the previous hidden state. So just from an equation and mathematical perspective, the way we design these outputs is like this. So A of t, which is basically some kind of an activation within my RNN, is B, which is my bias that we usually have, plus U x of t. U is the input weight essentially multiplying with the input sequence x of t, and you're adding W h t minus 1. So at every h of t, you are multiplying the previous h of t minus 1, and your hidden state is some nonlinear activation part of that. Right? So before we used to have z is equal to b plus w into x, your bias plus your weight multiplied by x. That is the same as a over here. And then you had a sigma of z is equal to some hidden layer representation, which is, in this case, we're just using tan h of a, but essentially it's the same part. The main difference that wasn't there before was this wh of t minus 1, the hidden state in the previous representation. Other parts are also the same. Your output is now c plus v of ht. So this is the same as your decoder, like a very linear decoder, and your output y of t is going to be softmax of o of t, which is what your output needs to be. In terms of design choices, your W, U, and V are nothing more than just linear layers in your multi-layer perceptron. Very simple. B and C are biases. So you can of course choose different nonlinear functions. It's not just tan h. You can use ReLU is probably most commonly used. So transition from hidden state to output can have multiple layers. So it's not just U, as I mentioned. It's U1, U2, V1, V2, V3, how many ever layers that you want. Again, softmax is something that you can omit. In many cases it is, because you want to make sure that whatever your x is, if its range is from 0 to let's say 25, that is not going to be possible in your output if you're using a softmax, because it's always going to give you 0 to 1. So you can change your soft output activation based on what you want your output to be. So of course, you need to decide on the dimensions of input, hidden state, and output vectors prior to training. And your different options in terms of encoding are one-hot encoding versus word embeddings. So word embeddings is not something that we are going to discuss today, but on Wednesday when we talk about transformers, we'll specifically talk about natural language processing. So we'll discuss what word embeddings and tokens are going to be. So your hidden state vector should be large enough to store condensed sequence information. We'll discuss more when we come to RNN architecture and LSTMs. And output vector dimensions are decided by the number of words it's possible to output. So in many cases, you are limited by your outputs. That is, your LLM can write an essay for you, but it cannot write like a 500-page essay, right? It could probably write like 2-page essay. So it's usually limited by the number of words that it can output, mainly because of this kind of architecture, where it has to have these kind of sequences from all the previous inputs and outputs. So it needs that state history, and it cannot have an infinite state history in terms of computationally. It'll be impossible. All right, any questions about the general RNNs themselves before we move on to loss and backpropagation? All right, yes. Mm-hmm. So it depends on what my x is going to be. In the simplest example I gave you, it is basically one character. T, H, and E, right? So essentially, it's nothing more than a vector. U and W is going to be nothing more than a vector. So your H of T minus 1, if this were a binary format, so number of characters are 26, so all you need is like what, like 5 numbers to represent T, H, and E. So it's just going to be 5 digits within your H, H in this case. But generally, that is not the case. Your X of T minus 1, X of T plus 1 is not going to be characters. It's going to be some kind of word embeddings, let's say in natural language processing, where we'll discuss more about this later, but essentially the dimensions of your X is going to influence how your H is going to be. It's very similar to in autoencoders, where in sparse autoencoders, we had the 784 cross 1 as our input, and then you blew it up to something like 2000 cross 1, right? You can have a similar architecture here as well, where H may not just be a number, it may be this kind of a vector of 2000 cross 1. No, so I'll discuss that right now, which is that it spreads out to the other weights. Technically, it's not spreading out, more that all these W's are the same. All these U's are the same, right? So essentially, it's kind of updating everything based on so it never looks at a column by itself. It needs to look at E, it needs to look at H and T all together. So that means that the loss function that we are going to be looking at is an average or a sum of all losses across the different, not columns, but branches essentially within this architecture. So that brings us to the next part of the lecture, which is, okay, how is loss and backpropagation actually done? So the backpropagation here has a unique name for itself, which is BPTT, which is backpropagation through time. The main idea behind this is that I need to now update across different characters, right? If I'm assuming that this is some kind of a character generation process, I'm looking at certain characters that are going to be coming in a sequence. So I'm getting T first, and then H, and then E, and so on. So I'll be looking at the loss of all the possible characters before I can decide what the loss is going to be. And the simplest way we can do it is just by adding it up. We can add all the losses across different branches, and that will be our total loss. And loss on each time step is contributing not only via the hidden state vector at that time step, but also on all the previous time steps that might exist. So work backwards through the last time step to obtain the full set of gradients, which essentially means that in our chain rule, when we have dou L by dou W, this is usually what we always have, we have dou L by dou output. So we are just separating these, we're just adding and multiplying by dou O here as well as dou O in the numerator and denominator. And then when we come to, ideally we want to come to dou W, right? So if we were doing this very simply with CNNs, dou L by dou W would be something like dou L by dou O multiplied by dou O by dou H, which would then be dou L by dou W multiplied by dou W by, sorry, I need to do H first. Dou H here multiplied by dou H by dou O multiplied by dou O by dou, what was this, like dou W. So dou H by dou W we're going to get by doing this. But the point here is that its H is not by itself. Like this would be a very self-contained equation in your CNNs. But when it comes to RNNs, your dou H by dou W, these two things are not as straightforward, right? So your dou H by dou W is going to be a combination across different branches within your RNN architecture. So we're going to be taking a sum here as well from tau equals 1 to t, which is from the first time step, if you consider this to be h of 1, to at the very end. So it'll be a sigma tau equals 1 to t, dou h by dou h tau multiplied by dou h tau by dou W, essentially, which means that we have more number of computations that we have to do across our backpropagation algorithm. We have to repeat LFT for all time t and examples I to obtain dou L by dou W. Again, everything we have talked about, at least the way I introduced it, was from a single word, T, H, and E, right? That's just one word, but that's just one example I. But there could be, ideally in your batch, there are going to be many sentences that you're going to be using. So all of them are all separate examples in this particular case. Again, this is like a, so this brings some kind of an issue, right? So we already have seen what vanishing gradient problem is. In CNNs, we encountered vanishing gradients problems because of the fact that we had a very deep architecture. We have ResNet, which has 101 layers, which have ResNets, which have 152 layers, right? So at the very end, when you're doing your backpropagation, your loss is quite high. It is easy to update your weights in the 151st layer, 150th layer, and so on. But as soon as you come down to, let's say, 10th layer, 9th layer, your gradients has now become almost zero. So it's not going to be changing at all. So if you visualize your weights, it's going to look nothing more than noise, and you're just fitting patterns to this noise function, which is not ideal. It's not generalizable or transferable at all. The vanishing gradient problem, however, in RNN is different. It's not based on the depth of the architecture, but the width of your edge, essentially, right? So in this case, even if we have single layers U and single layer V, if we have like 20,000 character depth, which is not uncommon in like your essays, papers, for instance, many times your characters are going to be as much. It's about like 6,000 to 12,000 is the character. 12,000 is the usual number of characters in like big journals. So if you want an LLM to write a paper for you, then that means that the width of this edge is going to be extremely large. Which essentially implies that you won't be able to get any gradients in the beginning. That means that your HFT mine plus 1, most of the loss is going to be considered here, while the previous loss is not going to be as much. The previous loss from that is also not going to be as much, and so on, right? So this is where the vanishing gradient problem comes in. For a large value of t, we are still doing our chain, long chain of our gradients, and as the sequence becomes longer, the product also gets bigger as well. And generally, this gradients are going to go towards 0. Now, if you want to take a mathematical approach to this, your output is going to be something like this: b plus wht minus 1 plus uxt minus 1, and you have some kind of a sigma. In this case, let's consider it a softmax. If that is the case, then if you backpropagate it, I've written that it's actually easy to see, but it's really, I mean, it kind of is, but it does require a little bit of math, but we're not as concerned with this math portion here. But essentially what you're doing mathematically is just multiplying the Jacobian of all your previous states and multiplying it with W transpose. It's nothing more than this: WHT minus 1 as a function of WH T minus 2 multiplied with something, right? And then WH of T minus 3 multiplied with something. If you want to get this entire sequence into a single matrix multiplication, it is this. JFT multiplied by WT is going to be the solution. So if you were to keep doing this across different sequences, you are going to become a long product chain, means gradients contributed from earlier time steps can quickly become 0 or close to 0, which implies that, I don't know, 20 or 30 characters from before, the gradients will not update themselves. There's going to be no output that you can get out of it, which means that your RNN only captures these kind of short-term dependencies that exist within the data. You cannot have like a very long term dependency that can exist within your data in this case. Again, this is a vanishing gradient problem, but it's different from what we saw in CNNs. It's not based on the depth. It's based on these recurrent features that now exist within my framework. Any questions about the vanishing gradient problem itself and how it's different from CNNs? So similarly to what we had done, so if you remember, AlexNet to VGG, when we went through, there's a couple of things that we had done. One was, instead of having a sigmoid or a tanh, we have like a ReLU activation function. Again, it helps in this particular case as well. So as you can see, this is the outputs, or this is the the gradients of different functions. The green, I think, is for tanh. Yes, the green is for tanh, blue is for sigmoid, and red is for a linear layer. Linear here, by the way. So if you look at the gradients of a ReLU function, anything less than 0, it is going to be 0. But after 0, your output itself is going to be linearly increasing, which implies that your gradient is a single number. Hence, what you see here is the gradient, which is the single number for a ReLU activation. Right, so ReLU helps quite a bit. Better weight initialization strategies as well. If you start off with some very small weight initialization strategies, it might not really update, or it might not contribute as much. So there's different ways. Again, identity matrix is one way of looking at this. There's many other weight initializations. I'm not sure if we'll get to this stage, at least in this course, where we'll be talking about these kind of timing initializations or other things, but maybe the last lecture can be there. But weight initializations by itself is a big deal. How we initialize the weights is a very important component as to how your neural network is going to train. All right, so maybe the way we are designing our RNNs is something that we can change. So these two things work, yes, but in isolation, they're very minor increments that can help, but they don't really help as much as we would want them to. So what we probably need is designing better recurrent units themselves. Self-connection specifically is probably the most important part, and having gates saying which of the inputs are important versus which are forgettable, let's say. And this is where a new type of architecture comes in, which is LSTMs, or long short-term memory networks. The goal in LSTMs is to determine what portions of the past history need to be forgotten. So many of the time when, in language processing or speech signals, there's a lot of redundancy that is involved when we speak. The same sentence gets repeated multiple times. In order to avoid that, at least for the purpose of storage and analysis within our networks, we want to be able to forget certain sections of the natural language or the text that we have been given. Right? So what portions of this past history need to be forgotten is very important. We can't forget the important parts, the summary. When we saw the example, we shouldn't be forgetting something like Peter, which is the most important, which talks about the noun within this text summarization process, right? So we need to know what needs to be forgotten, or in other words, we want to know what is the most attentive part that we need to be looking out for. And then we need to selectively update values and output only certain parts of these values. And this is between our present state HFT to the next state HFT plus 1. So this slide is of course a bit vague, but again, we're just talking about the motivation part here. We'll discuss more regarding what they mean specifically. All right, so in this case, LSTMs, which is long short-term memory networks, have this idea of an LSTM cell, where it tells you that your data, let's say language or speech, has to be analyzed in terms of cells, which then we need to use in terms of our outputs. So this entire thing is a cell, and this cell can be replicated. It's similar to the residual blocks that you saw in resonance. So each of those residual blocks can now be replicated across different algorithms, right? So similar thing is going to happen with LSTMs as well, where this particular cell can now be replicated across different sentences, across speech signals, and so on. In terms of design principles, there are three things, three gates: input gate, a forget gate, and an output gate. So input gate, let's start with the first one. Input gate is the one that you see here at the bottom. So it controls how much of the present input is allowed to factor into the computation. So very simply put, a lot of what I'm saying currently is dependent on what I said, let's say 2 or 3 sentences before. So how much is it that I'm adding to the overall discourse with my present sentence is what will be controlled by my input gate. So maybe you don't need to listen to the entire sentence currently. You just need to listen to 20% of the sentence that I'm currently saying now, as long as you know everything I've said until this point, right? So that is what your input gate is going to control. Forget gate controls how much of the old state is forgotten versus how much of it is important for the present state. So everything, how much time has it been? 15 minutes of my previous talking, maybe most of it is unimportant. Maybe you just need to retain like 5% of what I've said until now in order to be able to process what I'm going to be saying in the next state, which is h of t plus 1. Right? So that is controlled by something called a forget gate. And the last one is the output gate. It controls how much of the present output is influenced by the present state versus that of the past state. We haven't exactly discussed this, but essentially you can think of it as ot plus 1 is equal to f of ot comma x of t plus 1. Right? So generally we won't talk about this as much because we are going to be considering what we'll call a causal perspective in terms of our processing. So, but output gate does exist within the framework itself. Any question regarding the LSTM, the 3 gates, what the differences are? All right. An important design characteristic within an LSTM cell is this particular part here, which we'll be calling a self loop, right? So this is where in the previous RNN, a very simple RNN architecture, our x of t minus 1 was going up to h of t minus 1, which was then multiplied with w to get h of t, and then there was this x of t, right? So there was always a connection from the input of the previous state x of t minus 1 to h of t via h of t plus t minus 1. Another way to think about it is that the only way you can go from h of t minus 1 to h of t is when you had this kind of a x of t minus 1. The idea in LSTM is that you don't need to be connected to anything. You don't need to be connected to an x of t minus 1 in order to connect yourself to the next input. So your previous h of t minus 1 could be connected to your next gate or next set of inputs within the network itself, which is a little bit different than an RNN setup. What it does is it helps this kind of a gradient flow. So instead of having a recurrent network where your h of t plus 1 is dependent on h of t, which is actually dependent on h of t minus 1, which actually is dependent on h of t minus 2. So every single h of t is dependent on all the h of t's previously. Maybe that is not good from a vanishing gradient perspective, right? It's going to become 0. So instead of that, if you don't need to go through every single recurrent computation for getting h of t plus 1, maybe that is better. And that's where the self loop helps, where essentially you're just going to be looking at the past input. You're considering it more like a Markov model, where anything before that, it doesn't matter to me. It's just every single result I have in my previous h of t minus 1, I'm directly going to use it without having access to any of the x of t minus 2, h of t minus 2, and so on. So that kind of self loop, in fact, helps us within our computational perspective for our gradients. So currently, the state variable at current step s of t is a function of the previous s of t minus 1 via this internal kind of a self loop. Now, we have another gate here, which is called the forget gate, which is this portion. So just to be very clear, this is the input gate. This here was the forget gate, and this was the output gate. So looking at the forget gate, it's basically looking at the current input and all the previous states or the previous inputs. These gates, we call them gates, but essentially they're very simple multiplications. They're just element-wise multiplications. Given some kind of an old state A, B, C, D, I can now multiply it by, let's say, 1, 0, 0, 0, and that would mean that the only thing that would remain is an A, 0, 0, 0. Right? It's pretty straightforward in terms of what the outputs are going to be. So even though we call it like a forget gate, input gate, output gate, they're just, you can think of them as very simple weights that are being multiplied. And if the easiest thing you want to do with them is just to forget versus keep, then it could be this kind of a binary kind of a vector where it's 1, 0, 0, 0, where you'll forget the B, C, D and only remember the A, which basically your network has said that this is the most important element within my past state to move forward. These parameters, by the way, they're learnable parameters, so it's not like you have defined initially that the first state A is very important, so I'll keep it a 1, all the others are going to be 0. No, you have not said that. It's something that is going to be learned within a this kind of gradient descent framework, where you'll be learning this M, N, O, and P in order to construct your forget gate. So with that, we come to the update equation. I'd like you to look at this and again compare it to CNNs and to the RNNs, the base RNNs that we saw. CNNs, the only two things that is going to be required is B plus UXT. Of course, there's going to be a sigma there as well, which is going to be our nonlinearity. With RNNs, the only thing that you would have been looking at is an additional WHT minus 1, which essentially is where the recurrence was coming in. Now we have a couple of different things, which is the addition of these gates. So G of T is the input gate. It's telling us how much of this input I need to allow through. If I say that this gate is going to be 0, then that essentially means that the X of T input, whatever I'm saying, this present sentence is completely redundant. I wouldn't have to actually say the sentence at all for you to have understood all the previous ones. So in that case, you can consider your G of T to be 0, where every part of my input X of T is going to be irrelevant, and your network is never going to be using that in order to make any kind of a decision. Then there is a forget gate as well, where basically it's controlling the contribution from past state vectors, S of T minus 1, and of course S of T is your current state, and it could be an S of T plus 1, it will be controlled by this F of T, which is your forget gate. Again, we're not going to be directly looking at the output gate, at least in this particular case, but essentially it is going to be following a very similar philosophy. And the gate, of course, as we saw before, it's not simply just a set of binary functions, 1 and 0s, but rather it is a set of learnable parameters that we can then update during our recurrent neural network gradient descent algorithm that we'll be using. Of course, again, these are all parts of a cell. These cells can now be replicated across, and you can have multiple number of LSTM cells that is now going to be looking at your entire sequence in order to make some kind of a decision. Any question? All right. The output that we'll be looking at is a little bit more straightforward, which is Q of T. This gate is going to be, again, very similar. Your sigma, which is your nonlinearity, B naught, which is your bias, U X of T, W H of T minus 1 is going to be output gate in this particular case. And again, you're going to be using gradient descent to update the output gate as well. So this was the main architecture of LSTM. So we didn't go through the architecture of LSTM completely. We went through something called an LSTM cell, which is like the building block of like an LSTM network. But there are some inefficiencies that exist within your LSTMs as well. The most important one of which is the difference between the input and the forget gate. We are looking at the input and forget gate as two separate quantities. So if I go back here, your F of T and G of T are two separate set of parameters that we need to learn during gradient descent. What they're essentially doing is they are assigning a certain weight to my current input, which is your B plus UXT plus WHT minus 1. And then it is F of T is assigning a set of function to, or a set of weights to S of T minus 1. And both of them are being added, right? So you can think of it as, or at least one simple way of thinking about it is that maybe F of T plus G of T is going to be 1. In other words, I'm going to be taking 40% of my current input and 60% of my previous state in order to construct an output decision for this particular time state. That is how I can interpret this F of T plus G of T equals 1. And that is exactly what the next variant does, which is our GRUs, our gated gated recurrent units, where your GRU essentially states that you don't need to have an FFT, GFT separately. You can call it U of T, and then you can use 1 minus U of T within this kind of update equations, where again, the idea is very simple. If it's 40%, if it's in the current input, then all the previous inputs are taking about 60%, are using 60% of the previous states in order to find the current solution. A very straightforward and simple approach. Of course, what you get out of this is that you don't have GFT and FFT separately. Again, I gave a very simple example here when we did the MNOP and said that it's 1,000. These are long vectors. It could be a 2000 cross 1 vector, right? And these are replicated across different LSTM cells. So ideally, it helps a lot with your computation, where you are removing an entire gate and parameterizing the forget gate based on the input gate. It's just a 1 minus U of T. So in this case, the gate equations U of T, R of T, where your GRU is going to be helpful in terms of your computation. The reset gate. So there's going to be something called a reset gate in this case that you can use in order to define, and this reset gate is not something that is going to exist in every LSTM cell, but it can exist as part of a larger sequence. Let's say after 20 LSTM cells, you can have one reset gate and so on. But essentially, you have helped the computational complexity of your recurrent neural network by using these kind of redundant gates. Of course, there's many different variants of how these structures can be designed. So what we went through are the most basic RNNs, the most basic LSTM, and the most basic GRUs. But based on your application, you can have multiple ways of designing this. This first one here is an MLP. Very simple. You have an input, you have some hidden layer representation, and you have an output. It's just vector matrices that are multiplying them. The next one is one-to-many, given a single sequence. Let's say you have a sentence in English, you can translate that into multiple other languages, right? It could be French, Spanish, Hindi, Urdu. So many different languages can now be translated into. Or it could be a many-to-one translation. There could be a many-to-many, many-to-many again, based on the structure of how you have defined all these hidden representations. Or this could be like an LSTM cell and so on. So based on these configurations, you could have multiple ways of designing your recurrent neural networks. We won't go through all of them, of course, but this is just one set of possible ways of designing RNNs. Any questions? Next, we'll move on to something called convolutional networks, or temporal convolutional networks. Before that, if anybody has any questions on RNNs, we can take that and then move on. All right, so all recurrent neural networks, they still suffer from a few problems, 4 of which are parallelism, receptive field, gradient stability, and training time memory. Parallelism is essentially where future time steps must wait for earlier time steps because you need state vectors, right? So for every x of t, I still need an x of t minus 25, let's say, the computation for that. And this is going to exponentially increase over time. Maybe not exponentially, linearly increase over time, where x of t plus 3000 is dependent on x of the current t. Right? Of course, you can use a gate in order to reduce this, but during training, the gate is trained. So the gate needs to learn that 3000 before it needs to be a 0. So it's not easy to create like parallel architectures, or you cannot parallelize the training process in RNNs quite easily. The next is the receptive field. If you remember what this meant when we talked about CNNs, it's that in the first layer of a CNN, the network is looking at just a 3x3 kernel. So it knows, every kernel knows what is happening in that 3x3 vicinity, but it does not know anything else on the side. But when you come to a second layer, it's looking at the output of the current 3x3 and the next stride convolution of the next 3x3 and one after that. So it basically has a bigger receptive field within the input. The way you can get the complete receptive field for the input is by having a very deep architecture. right? So unfortunately, that is not something that we can do with RNNs. We know that the amount of receptive field that we can get is dependent on our weight matrix, our UV. So we cannot have a very large receptive field when we are discussing these kind of RNNs. We have to have these wide architectures rather than deep architectures. This also causes problem with the training time and memory as well. So again, memory requirement is very large depending on the sequence length. And the gradient stability as well. Long input sequences can have unstable gradients. So maybe there is a possibility of using convolutional neural networks here that we are going to be calling 1D temporal convolutional networks in order to do this. Computation in these kind of temporal convolutional networks is straightforward and simple, mainly because it's a very simple linear process. Even though when we look at this 1, 2, 3, 4 convolved with something like 1 and 2, and we think that this is a difficult process, it's really not that difficult from a matrix perspective. You can create a templates matrix. So your 1, 2, 3, 4 is now this vector here, and you can take 1, 2 and create this kind of a matrix. You know, your 1, 2 here, and if you have 1, 2, 3, 4, if you have 0, 0, your first element is going to be 1 multiplied by 1, and then 2 multiplied by 2, 0 multiplied by 0, and 0 multiplied by 0, right? So it's a much easier matrix multiplication process when you consider that the next one is going to be zeros here, 0, 0, 1, 2. So this is going to be multiplied by this, and so on. So it's you can take your convolution operation and convert it into a simple matrix operation by taking this input and converting it into this kind of a very specific templates matrix. We call this structure as a templates matrix, by the way. So computationally, it is simple. 1D convolution is very simple for something like PyTorch, MATLAB. It's nothing more than simple matrix multiplications. Convolution by design helps us increase the receptive field. So before, the issue with RNNs and receptive field was that the receptive field could not be increased, right, because of depth. So what we can do in convolution is have this additional thing called dilated convolution that is going to help us increase our receptive field. What dilated convolution means is, till now, let me expand this, zoom this in. So any convolution that we have seen is something like this, where I have a 3x3 kernel, which is going to multiply every single element here, add that element, and convert it into a single element here, right? But maybe we don't need every single element to be multiplied. We can still construct a 3x3 kernel, which is the same as this, and say that there needs to be holes in between. So we don't want these elements within our input to be involved within our computation part. That is essentially what we mean by dilated convolution. And the reason here that we can do this is, again, in vision, it's very straightforward. You're basically just downsampling it within the kernels rather than downsampling it 1080p image to a 224 image and then passing it through a network. Your network is itself downsampling your image within the framework, right? So your receptive field is right now this kind of 6x6 rather than a 3x3 framework. Of course, you can increase your dilation and say that you need a 2 pixel width between every time you look at it. And convolution gives us a simple way of increasing our receptive field without increasing our depth. Again, all of this, the goal of doing all of this is to we start talking about this receptive field limitation here that exists within RNNs that can be overcome by using something like convolutional networks. Computational complexity. So CNNs only use a fixed set of kernels per layer. So you already know this. We have a 3x3, let's say a kernel that is going to be independent of your input. If your input, for instance, in vision was a 1080p image, your 3x3 would just have more number of computations in terms of convolution, but the size 3x3 itself is not going to change. It's still going to remain the exact same, which is kind of different from RNNs, where you need to, it's dependent on the input. So your network is itself dependent on the input number of images, which adds to the computational bottleneck. The last one, of course, is that gradients in an RNN The vanishing gradients happen in this kind of a horizontal framework, but if we have a CNN that we are using here, we can go back to what we had with vision. We had a lot of methodologies, right? Like dropout, for instance, which would help us in terms of overfitting, even the vanishing gradient problems in terms of residual blocks, that also would help us. So we can bring back all the residual connections and everything in order to help us with this kind of a vanishing gradient problem. So that would help as well. So these are some of the advantages that we have in these kind of temporal convolution networks. Input sequence invariability. Again, this is dependent on the fact that your convolution is looking as templates. It looks at the kernel, it learns the kernels, and it tries to find these kernels as templates within your input image. This is a very important phrase here, which is causal sequence modeling. If you were to go online and just type in causal machine learning or causality in machine learning, there's a very deep rabbit hole essentially, where this is going to lead you into something like structured causal models, interventions, and so on. But in this lecture, in this course, in fact, when we are talking about causality, causality comes from a signal processing perspective, where causal essentially implies that the current the current output is going to be dependent on the current input and all the previous inputs. It's not going to be dependent on anything I am going to say later. And in a way, it makes a lot of sense, because that's how processing needs to happen, right? We won't have access to future inputs. So what is the point of even thinking about non-causality in this case, which is that when you are analyzing something right now, it depends on all the information that you have, not based on what the information that might come later down the line. So that is essentially what we are talking about in terms of causal sequence modeling. But I mean, intuitively it makes sense, but it might, there are cases where this is not true. For instance, maybe I spoke about something 5 minutes back. You did not understand it then, but the way the slides are designed is that there's a little bit of redundancy here, where I'll talk about the same thing again 2-3 slides from now. So you might understand what I talked about like 5 minutes before by listening to what I'm going to be talking about now. So the processing that you need to have done 5 minutes is dependent on the future time step of what I'll be speaking about. So it's not always clear whether causal sequence modeling should happen, but it does help computational complexity, and CNNs do give you the option of having this kind of a causal sequence model. We'll be talking about in terms of padding and dilation, which is a very straightforward and very important like signal processing technique that we use. And residual units for ease of optimization. So again, similar to LSTM cells, we'll have convolutional cells as well. We're going to be calling it TCN, and we'll be using it within our computational framework. And optimal receptive field design. So this is the most important one, where we can design based on the amount of dilation we have, we can design the receptive field within our sequence framework. All right, there's a few slides today, but maybe we'll go through this on Wednesday. But essentially, it's just going to connect everything that we have talked about into one cell, which is this kind of a TCN cell, which is going to be similar to that LSTM we discussed. But we'll go through more of this on Wednesday. That's the end of lecture for today.